In this video, we are going to talk about wireless, and especially we are going to focus on Bluetooth, Wi-Fi, and cellular. And we are going to compare what are the differences, when we would like to use specific technology, and basically this is what we are going to talk about, Frida, correct?
Yes.
Okay. So tell us a little bit about yourself. Why this is your like hobby, job, or why you are into wireless?
Um, Thank you for the invitation. First of all, it's a privilege being here. And my name is Frida. I have been a firmware developer for a little bit more than 3 years and a half. And before that, I was a firmware supervisor for RN and R&D engineering team. So I've been working in the embedded industry for a little bit now, and uh, it's more a professional background, but at the same time, it's a little bit of a hobby. I am passionate about technology, so maybe I haven't worked with all protocols, but I've learned some things from other protocols just by doing some personal research because I get bored and I want to know more. That's pretty much the reason. And yep, that's, I guess that covers it. So yeah, I would like to have a conversation with you today regarding the three most popular protocols,
Okay,
or
I'm
at
going
least
to
the ones
interrupt
that
you.
I've been
I'm going to
working with.
interrupt you. So,
Yep.
so you basically know how to write the software, the firmware, which is actually kind of handling these protocols?
Yeah, for cellular, yes. For Wi-Fi, I've only seen some implementations, but I haven't actually written code. And for Bluetooth, I'm basically a user. I haven't actually I've only seen the SDK from ST that they have for Bluetooth, but I haven't actually written code for Bluetooth.
So you are
Um,
one of the people who are the important people making these connections.
Well, I mean, the different organizations that drive the technical specifications, yeah, those are commonly known, but I've been fortunate enough to work with people that have been working with these stacks on the firmware side for a long time, for minimum of 15 years.
Many people, when they are deciding if use Bluetooth, Wi-Fi, or cellular, is or at least what I would do is like, oh, do I need internet connection? No, so I go for Bluetooth, for example. Or do I need like a very low power or something? Then maybe I go for Bluetooth. Do I need internet? Maybe I go for Wi-Fi. But cellular is a little bit tricky. I used it once when I knew my product is going to be somewhere in country. But this is basically how I make decisions. But today we would like to go a little bit deeper. We would like to understand a little bit deeper what are the differences, because maybe you don't want to use Wi-Fi, maybe you would like to use cellular. So that's exactly what is here in this table, and you are going to explain.
Yep, yep. We're going to explain it throughout the presentation, but yes, that's the goal. Um, Let me just get started here with
Okay,
some technicalities first so
okay.
that we can understand a little bit more each one and see where that takes us. So first of all, wireless protocols means we don't have a physical a cable, a physical mean to transmit data. We're going to use the air. And these three protocols are going to work based on that. We're going to transmit information throughout the air. And for that, we need to transmit via frequency bands. And Bluetooth uses 2.4 gigahertz. That's an unlicensed band. Wi-Fi varies depending on the generation of Wi-Fi and the implementation. So 2.456 gigahertz, and the newer ones, 6E and 7, which are basically on research stage, but they will,
Oh,
or they are,
I didn't know they used 6 gigahertz. So
yeah, it's
this is
on
the Wi-Fi
research.
6.
Yeah, it's still in research. I haven't heard about actual implementations, but the idea is to continue improving each protocol, right? So right now we have deployments for
Mm-hmm.
5 gigahertz, for example. Yeah.
Okay, you can
Um,
continue.
cellular. Cellular is interesting. So basically, in cellular technologies, there is a concept, a definition called carriers. Carriers are basically companies who own a piece of the frequency spectrum that allows them to use certain bands. But all of them, if we generalize them, they use sub 6 gigahertz and millimeter wave. That's a different implementation, but still cellular uses those that frequency range
24 to
and
100 gigahertz.
24 to 100 gigahertz. And well, maximum data rate, like how fast are we sending data? Uh, Bluetooth, all these protocols, as I mentioned, have generations. So BT means Bluetooth Classic, and BLE means Bluetooth Low Energy. Uh, Bluetooth Classic can do 2 megabits per second. BLE, it's a little bit slower, can be a little bit slower. Uh, Wi-Fi, Wi-Fi,
Do you know more information about this Bluetooth? Because I see different generations many times, and I'm like, do I really need to know if I have the newest version or the old one were really bad, or Bluetooth low energy? I need to have it on my headphones, or what are the differences?
yeah, yeah. So, in theory, all these generations should be backwards compatible.
Mm-hmm.
So we should be able to talk Bluetooth 4 with Bluetooth 5 and sort of like that. Bluetooth Low Energy has a slightly different implementation. The idea of Bluetooth Low Energy is to um, have devices that need to prioritize battery life. So for that, you're aiming to make power efficiency uh, the utmost important requirement. So for that, you need to compromise the amount of data you're sending, the speed to which you're sending it. So um, it is it is important in the sense that if you have a product that you want to launch and it's using a specific generation, you want to make sure that it's not so outdated that it's not going to be able to communicate with your network, right?
Mm-hmm.
So just staying in the latest as with usual,
Mm-hmm.
that's usually a good way to go.
So this Bluetooth Low Energy, do you know if what is different? Like is like protocol a little bit different, or the way how it communicates, or
So, for example, one of the things that is different is on channel access. Classic Bluetooth uses frequency hopping spread spectrum, which is an older technology. In Bluetooth, they have channel access is basically the way we administer how we transmit data without intercepting with other devices.
mm-hmm.
So, um, an improvement of frequency hopping with that algorithm is implemented in Bluetooth Low Energy so that we can have some gains on how we're transmitting data so that we can save energy.
Mm-hmm. So
Yeah.
the frequency hopping, what you just mentioned, this is something interesting because I never really went into this. So I just would like to confirm. So it means even if it's like kind of one frequency, there are like kind of like multiple channels which can be used between different
Yeah.
devices, different channels, or because I think this is similar for Wi-Fi, correct?
Yeah. They all wireless technologies are based on the primary idea of frequency hopping in different implementations. But yes, the idea is to um, uh, make the most of the bandwidth that exists so that we can make the most on each protocol, but each protocol has its own requirements, so they're going to use that smartness differently.
Mm-hmm.
Yeah.
Okay, okay, we can continue.
Okay. Well, Wi-Fi, Wi-Fi 6, we see significantly
9.6
faster. Yeah,
giga.
faster speeds. And seven.
That's even faster than like wired Ethernet. No?
Yeah, yeah. Actually, if you do speed tests on your normal laptop with the wired connection, you're gonna see like what 300 megabits per second, or maybe and maybe I'm just paying very cheap my internet, and that's why I have crappy internet. But anyways, yeah, the idea is for these wider wireless protocols to connect more devices, without the restriction of the wiring. In environment, infrastructure, and still be able to deliver faster speeds.
Oh,
Yeah,
that's interesting. That's very
yeah,
interesting table. I never really just compared the numbers like this.
yeah, yeah, yeah. It's definitely it's a complex world, but it's definitely an interesting one.
Five
Uh,
5 gig, 20 giga. Wow.
yeah, yeah. And what's interesting here is that cellular technology relies on having external base stations. So base stations are um, setups with radios and antennas. So your phone, usually all of us have phones normally in this era. So your phone is going to connect to a base station somewhere, and then it's going to interact with it somehow. Um, and the idea is that the interaction between your phone and that base station is going to give you that throughput, which is basically what we're going to see in the different frequency bands. Depending on the frequency band that you're working with, you're going to see these speeds. If you're using 5G or 4G, you can see 1 gigabits per second.
Now I'm curious. So, is this speed depending on something? I don't distance from the base or something. I don't know.
Throughput will degrade if the base station is too far. That's why, for example, if we're looking at an agricultural applic yeah, an application that is meant to be in an agricultural place, you need to be really smart of if you want to use that because you're probably just not gonna get the performance of the throughput that you're gonna need because the base stations are just too far away, they're too little. With difference in the city, you're gonna have base stations everywhere.
Mm-hmm.
You basically have a really good coverage for any device that you want to connect.
Mm-hmm.
Um, that's, for example, one idea on why you would choose one protocol over another one. Uh, Typical range. This is important. Depending on how far your devices are, you want to note this quality. Bluetooth class 2 can extend up to 10 meters. So you have devices talking to each other in that distance. And class 1 can go up to 100 meters.
100. I didn't know 100 meters.
And these are all theoretical numbers. You're gonna see a lot of numbers here, but the whole idea of the magnitude and the order of these numbers are what gives you the the understanding of why each technology is different from the other one.
So I would
Uh,
expect. So what is difference between class one, class two? Which one is like latest one, or there is? It's not like latest one. There is different in technology what they are using.
to be honest, I'm not particularly sure.
Okay.
I I just know that there are some implementations that make the transfer in a way that you can extend it for the distance
Mm-hmm.
that you need, but the physical restriction doesn't go beyond that.
Mm-hmm. Okay.
Yeah.
So important is to mention this. So if someone decide for Bluetooth, they know. Okay, let's going to search for class one because this one can go up to 100 meters, and then they can search by themselves. Okay.
Uh,
Next.
Wi-Fi. Usually, Bluetooth devices are tending to have a line of sight, meaning there are no
Walls.
physical. barriers, for example, walls or stuff like that. Wi-Fi, we usually have Wi-Fi devices on our homes. We have doors, walls, whatever, buildings. So the line of sight is not necessarily complied. So that's why we have a different capability to reach far farther distances um, for Wi-Fi indoors and outdoors environment. And Wi-Fi 6, I don't know what the number is, but it's supposedly gonna improve what we have today on Wi-Fi 5, for example.
I'm curious what will happen. And I would like to add, I think I remember the days when internet was kind of starting. I'm that old. And I remember, for example, we used to use Wi-Fi with special antennas, like for like much longer transfer than just only 120 meters. So it may depends also on what kind of antenna we use. But I don't know if it's like allowed by, I don't know.
Yeah, the RF design is a science on its own, right? The way you design your antennas, how much power you can supply to them. Do you have the uh, power infrastructure to service that device? Um, do you do it without interfering with any other components within your device? That's that's why people get paid the big bucks, I guess.
Uh,
Um,
Next one, okay.
oh, microcells. So cellular technology, we have gone from a certain distance, then we extended it in Wi-Fi, and cellular is the one that can reach the longest distance. Doesn't mean necessarily that it's going to service your throughput as you need it, but it's theoretically supposed to cover that long distance, which is in the order of kilometers now. If we think of beehives, cell base stations work a little bit like that. If you have different base stations, they're gonna create this beehive. So if you're unlucky enough to fall within one of the limits of the small hexagons,
Mm-hmm.
then you're gonna be serviced by one or the other. And the cellular technology has policies to say this is the way we're gonna service that specific um, um, scenario. And the idea is that if you have macrocells, you have bigger hives,
Mm-hmm.
bigger hexagons, and if you have small cells, your base station is has lower capabilities, but it is still able to create this ultimate hive to service whatever devices you have within your network.
So do you know where these small cells will be used? Because 10 meters looks very small to me.
That's a good question. I don't know. I don't know what the practical implementation would be here.
Mm-hmm.
Yeah.
Okay, we can continue. This one is important. Power consumption.
Yep. This is we've discussed distance. I think that's one important difference between protocols. It becomes obvious with the numbers. The other one is power consumption. Uh, Bluetooth is we're supposedly with Bluetooth Classic and Bluetooth Low Energy, we're servicing um, a smaller amount of devices within a smaller reach. So we shouldn't be using so much power. So that's the whole idea. And Bluetooth Low Energy champions the idea that it uses the least amount of energy to do all of the interactions that it needs to do for pairing, for transmitting data, for communicating with other devices. So that one is in milliwatts order, um, 1 to 10 milliwatts order. Wi-Fi, we are going higher in what we need to satisfy the stack needs. So we need 100, 800 milliwatts. And for cellular, we use 1 to 3 watts, varies by signal, but we can definitely see that the we're changing the order of magnitude that we need to
Yeah,
make use of the technology. Usually, it's not a rule, but usually cellular devices may or may not have battery um, components. For example, phones do use them, but if you're looking for a bigger device, a higher a device that has more features, for example, an access point, a router, that usually does not um, implement a battery hardware component. It implements a wall power outlet because it's gonna need continuous energy and a significant amount of energy to to make the communication reliable and and active.
I have a question about this. Again, I don't know if you will know the answer. So I think at least cellular they can negotiate the power or something. I don't know. Or
The,
basically, when you are closer, then maybe you don't need so high power. Or
yeah, yeah. If you're not transmitting data, there is logic in the code that allows you to just put the device on its uh, minimum needs so that it transmits whatever it needs to transmit to continue having um, the session active, the the communication session active. Uh, but it's not going to be the same as the energy that you need to use when you're actually streaming a video or
mm-hmm,
transferring so much data that you need to have your um, peripherals on TX, RX all the time, receiving and interacting with the data.
mm-hmm,
Um, there are also other policies. For example, I don't know if I can say company names here, but I'm gonna say it. Microsoft has mobile band specifications, MBIM, that tells you when you should, or when you must uh, enter an idle state, when you can be on active, and when you can do that, which operations are allowed. All of that is described in an open source Microsoft Learn um, documentation. So um, it depends on some regulatory um, requirements of depending on the product that you're doing. You can have other um, power consumption rules
mm-hmm.
to comply with.
Is there something also about the signal power? Because what we are talking about right now, I think it's a lot connected also to whole system power, like maybe the chip and everything. But I was thinking maybe there is also something about how strong the signal is. I don't know.
For
For the
transmission,
radio, yes, exactly.
yeah, there it's
So it's
that's
not always 3 watts, but if you are closer, it can be, I don't know, 1 watt. I don't know. I have no idea. I'm just
yeah,
guessing.
yeah. It's more like in terms of the signal strength, we have our SSI metrics. There are a lot of measurements within the the technical specifications that dictate how the protocol works in terms of all these concepts is 3GPP. So that tells you if it has some pretty interesting heavy math, but it basically tells you that based on these calculations, we're gonna say that there's gonna be this maximum transmit power,
Mm-hmm.
and depending on what you're using in the bands, um, this signal strength that is expected. This is the throughput that is expected with that
Mm-hmm.
signal, mm, not specifically the signal strength, but all the metrics that you need to comply with for the for the protocol.
So now tricky question. So does it mean the cellular can have maybe same power consumption as Wi-Fi?
In some cases, it could. Uh, depending on what your application is. Um, in some specific cases, it could, but if you're doing that, then you're probably gonna have to raise a question to say maybe there could be another technology that we could have researched or prototyped that could have made our product cheaper,
Mm-hmm.
and that could have been sufficient, and that could have made our product more
Oh,
rentable.
is price included here in the table?
No, we're gonna talk a little bit about
Ah,
that
okay.
in the next
Next
slides,
one.
but
Okay.
uh, it's that yeah, the if you're gonna invest in one of these technologies, you're gonna need more investment from if we see this slide from left to right, there's more investment
Mm-hmm.
as we go from left to right.
Mm-hmm. We can move to the
Yeah.
next one. So modulation. I have no idea about this. So you can explain.
Modulation. So in rough terms, modulation is we send bits via the air. So basically, the conversion of how that data is sent in those bits, that's what modulation is. And these are fancy terms for example, GFSK is Gaussian frequency shifting key. So the way you modulate, the way you form what you're transmitting, it's done in a certain way
Mm-hmm.
mathematically. Um, for example, we could also have differential quadrature phase shifting, which instead of doing frequency, you're doing phase modulation um, for the signal that you're transmitting. And for Wi-Fi, it is popular that they use orthogonal frequency division multiplexing. That's the name of the mathematical algorithm that does the form um, for the transmission. And we also have quadrature amplitude modulation. MIMO is multiple input, multiple outputs. Depending on your device, you can have multiple antennas, so you're gonna have a different scheme um, to to manage that modulation. And beamforming, I'm gonna mention it more towards cellular. In one of the latest generations of 5G, instead of having these hives radiate signal to have coverage, you can do dots and sweeps around the circle so that you can have it's another way to service devices to not have that red radiation, it's not radiation, that diffusion of service all the time, but it is done in a different way, smarter way, in which you can just sweep the area with these shots of of uh, of signals.
Mm-hmm. So basically,
Um,
you don't need to kind of waste energy everywhere, but you find where are the devices and you focus the transmission directly between in these directions.
exactly.
Okay.
I couldn't have said it better, man. Uh, exactly. And for that, OFDMA is basically multiple users doing OFDM. So um, orthogonal frequency division multiple access. That's what OFDM stands for. And it's usually done for downlink when we're getting data into the device. And SCFDMA is done for single carrier frequency division, multiple access. Basically, it's another mathematical way to do um, the modulation for uplink, usually. So we're sending information from the device to the base station.
Is there some, I don't know, preference? So I'm going to buy new Wi-Fi. I would like to have beamforming because that's the best. I don't know.
I don't To be honest, I don't know about beamforming on Wi-Fi, but definitely for cellular, if you're doing beamforming, that means you're doing millimeter wave. So that is going to give you, you're going to need a chipset that can do millimeter wave, and you're going to need a hardware RF design that allows you to do that with your device.
I guess the antenna must be maybe like antenna arrays, or I have no idea.
Yeah, it's there are there are specific RF requirements that need to be met for each implementation.
Hmm.
Yeah.
Okay, next, channel access. Again, I have no
Uh,
idea what this is.
Channel access. We discussed it a little bit before, as basically we are trying to send data without interfering with each other, and we're
Hmm.
using the same medium. So that's why we need to have the specific sequences to do that. And in this case, Bluetooth Classic uses frequency hopping spectrum. Bluetooth Low Energy uses a variation of that, but it's based on the same frequency hopping principle.
But
Uh,
I would like to just clarify. So it means uh, Bluetooth is at 2.4, but there is some kind of bandwidth. So frequency hopping, it means the Bluetooth works on, for example, I'm going to just say example, 2.41, then 2.42, 2.43. So 10 devices can work with 10 channels.
yes,
Okay.
yes. Yeah, it's a here it's simplified, but the fact that it works within 2.4 gigahertz doesn't mean that it only works in
Hmm.
that specific number. We have a range, right? So we need to use that range in a smart way.
Hmm.
Yeah. Yep. Um, CSMA, that's carrier sense multiple access with collision avoidance. Again, we're using the same medium, so um, this algorithm has to have a specific separation to, in the case where we do collide, how do we address that, and how do we avoid it from happening in the first place?
I was actually thinking about this because, all the days you turn off or turn on a Wi-Fi router, and there was your network and maybe your neighbor network. So I think there are also channels. So you could say, "Oh, I'm going to use this channel, and neighbor is using this channel." Perfect. But now in apartment buildings, you switch on your router, and there are 30 Wi-Fi networks. So I was thinking how it
Yes.
works.
There is more like when we're gonna see the architecture layer a little bit of from a firmware perspective. We have more. We have authentication, right? You ideally you don't know your neighbor's password or credentials, right? So even though you're using the same bandwidth, the same frequency bands, that's more proper. Um, you it doesn't matter. Your router only allows you to have access to a certain network,
Mhm.
right? So you're gonna have authentication. You're gonna have more things on the upper higher level protocol that allows you to just make use of that, but not use your neighbor's router for that.
But what if there are too many routers and they would like to use exactly same frequency? Are they not going to like fight together?
No, I mean, there is definitely network congestion at some point. We're gonna see it with if you look at how people are using the bandwidth in worldwide, you're gonna see more interactions during workdays than in the weekends. Similar as what happens with electricity. You can have peak hours and sort of those, but the whole idea for internet service providers is that even though we do have that network congestion because we have multiple users and it's gonna get crowded at some points. We are supposed to have the service that we each company provider guarantees. So if you're going to have whatever megabits per second for your plan, then you're going to have that the company is supposedly working
Mm-hmm.
to do that. And your hardware requirements, that's from the service side. But from your device, there is logic that allows you to not, even if we do see some network congestion across devices and within different networks, um, we are able to segregate
Mm-hmm.
and service
So there are some
what
techniques
we
how to
need.
handle these
Yeah,
situations. Yeah.
yeah,
So
yeah.
these are also these like these
Methods.
CSMA. Yeah,
Yeah,
that's
yeah.
exact.
They are
Okay.
methods. Yeah, yeah.
Okay. Uh,
And cellular. Sorry?
yeah. Yeah. Go ahead.
Cellular is network coordinated. It's a little bit more complex, but basically, different layers allow us to get the medium access we need, and that is driven by the network. So the whatever the carrier, whichever policies the carrier has set up, we can make use of them.
Mm-hmm.
Uh, Latency. Latency is the time
You
that
you know
takes us.
I'm sorry for interrupting. This was very interesting row when I was checking your slides before recording. This was one of the most interesting ones.
No. Uh, it's promising for newer technologies. I'm gonna get there in when I get to the cellular block. But latency is a time that takes us to get a reply from the network for the interaction that we have on with the network. So, and I'm gonna say this very conservatively. This is basically a time constraint, which in within each protocol. So it's not that rigid, and that's the part that is conservative because we do have in the hardware, we're going to see it, but we have interruptions that we need to service on a strict timing so that the protocol works well. Well, but in here we can see from the order of magnitude and the numeric the number the numerous numbers that we're using, that is it goes again, from slower to faster service from Bluetooth to cellular, left to right. So basically 40 to 100 milliseconds for Bluetooth, classic, for example, for Wi-Fi, 1 to 5 milliseconds. That means it's faster. When we are not connecting to the internet, local networks means we're just pinging computers within our own
Mm-hmm.
local
Network.
network, our
Mm-hmm.
own reach. And internet means we're pinging some public IP somewhere, right? So it's going to be faster. It takes longer to get there. So 10, 15, 50 milliseconds. For cellular, 5G is less than 1 millisecond, and this is key. One of the reasons why generations have evolved in cellular technology is for uh, critical mission applications to be serviced and satisfied. URLLC is an a new technology that it means ultra reliable low latency. So this one is used or is targeting to be used in autonomous driving.
Mm-hmm. I was exactly
Ideally,
thinking what could be the application because it has to be some kind
yeah,
of real time application.
yeah, ideally, autonomous driving needs to be flawless to avoid any type of disruption. That is a mission critical application. And if you want the, the car to stop flawlessly, then you have to be able to respond quickly to all the interactions that are happening in the network. So that is one application. 4G can be a little bit slower. It just targets general use. So 10, 50 milliseconds.
Mm-hmm. Actually,
Yeah.
when I see 200 milliseconds on Bluetooth, I remember when I had sometimes when I connected my headphones to some computers, then I could see the difference between mouth and sound, and it was so annoying.
Yeah, yeah, it's interesting.
200 milliseconds is a lot. You can actually
Yes,
notice
yes,
the
yes.
difference.
Yeah, you wouldn't use this type of technology. Knowing this, you wouldn't use it for
Yeah,
mission critical or time constrained applications, right?
yeah.
Yeah,
I'm sure
yeah,
it's somehow fixed now because everyone is using headphones.
yeah,
That's no
yeah.
problem. But I think
There,
what also add, because maybe we are talking about the communication between the chips or modems or something, but then there is maybe software and some other stuff. It will add and add and add the delay, and finally it maybe doesn't have to be 200 milliseconds. It can be actually even more between like high
the
level
whole
application
system.
code. Yeah.
Yes, yes, definitely. Yeah.
Mm.
Maximum connections. That one is a little bit true and not. So remember, each protocol has its types or flavors. So 7 to 8 active devices, that's for the Bluetooth Piconet type. So that's a limitation, but Bluetooth Classic can connect up to, I think, more than 200 devices at
Hmm.
the same time. So Wi-Fi, 200 plus devices per access point. Each one gets a specific
I guess
bandwidth.
that's like theoretical. I don't know how fast everything would be then.
Yeah, yeah, usually like households, if you think of a person having one computer, one cell phone, uh, 4 people, that's only 8 devices. You
Yeah,
far from 250, and we're going we're going a little bit hypothetical here. But even if we double that, that's
but
still
maybe
not
some
250.
hotels or airports or I don't know.
Maybe. But for that, um, they would have a different infrastructure. For example, they would have an access point. An access point is actually what we have in our houses, right? The tiny little modem. So hotels would have more than that one access point for sure.
Yeah,
Uh, yep. Okay. Wow, cellular. Again, the evolution of cellular wants to connect as much as devices exist. There is a number on the billions of devices that are going to be available in this year and in the next one. So the idea for cellular is to to service them all for all IoT applications. So yep, 1 million plus devices.
I don't know how they do that actually. I was thinking about this because when you have like really big cities, there are like millions of people living in one city. Of course, you need to have base everywhere,
Infrastructure.
but
Yeah.
still, everyone is everyone has smartphones, and there must be so many connections.
Yeah. Yeah. And that's why, again, the evolution of the technology goes because there are always better ways or enhanced ways to use the spectrum. So people keep proposing new stuff or
Hmm.
improvements to what we have today to be able to do that, to service them all. Yeah,
It probably it must be done because if maybe 5G is not coming, or if it was not developed, maybe in these days the old technologies they would not be even able to handle so many. I don't know.
definitely. Definitely true. And I mean, I'm more into cellular technologies because of professional work, but the truth is, for the research that they are doing for Wi-Fi 6, they are aiming for the same thing. They are aiming to be able to service as much devices as possible. Yeah.
Okay, next security. Okay.
Oof. Okay, so today it is very, very hard to find a device that is not hackable. So um, all these protocols will use different policies and will satisfy general security rules, all of them, so that we are able to guarantee a security level for the devices, right? So in this case, uh, Bluetooth uses AES, that's a symmetric block cipher. Um, and remember, if anyone has paired a Bluetooth device, which I guess everyone has, you get a PIN when you do that pairing for the first time. So all of those authentication and all of those steps guarantee that yes, this is I am the user that wants to use this device with this network and establish this communication between devices. Um, okay, so Wi-Fi has its own security algorithms, methodologies, WPA3. The way this is basic when you go into your router and want to connect to the internet, you go and enter some credentials,
Yeah.
and in there, it doesn't it doesn't do it anymore, but in older routers, and if you go into the advanced configuration of the router, you're gonna see that there are different methods you can use for this authentication methods that you can choose from. And it has a different uh, same same block cipher as before, but with more bits to use. And cellular, I mentioned 3GPP is the organism that lays out all the policies, how the technology should be used. So they establish the rules that we need to satisfy to be able to connect to the network. For example, when you're using your phone, usually SIM cards have these tiny yellow pads. Those are basically um, we can think of them like rough, simple storage cards. So those SIM cards get delivered to you by your telephony company, and then that SIM card has a specific phone number, and it has more information within its file system that allows to say, oh, this is a recognized device that is connecting to my network. It's not just some random uh, SIM card connecting or trying to use my infrastructure. Yeah,
Mm-hmm. Yeah.
yeah.
Okay, next.
Um,
Current standards.
Current standards, that's basically where we are at. Bluetooth 5.4 is the latest generation in Classic. We have Bluetooth Low Energy existing, and there's also another flavor of Bluetooth called Bluetooth Mesh. In which there is redundancy within devices, so that we can have a more robust interaction and communication without depending so much on a master device, let's say.
I didn't know it exists in Bluetooth. So it means if you have more Bluetooth devices, for example, in your home, they can connect with each other and transfer signal to the one
Yeah,
which
that's the
is
idea.
furthest.
Yeah, that's the idea.
I didn't know it's in Bluetooth.
Yeah, yeah, there is an implementation for it. Wi-Fi 6, a 7, I haven't seen real time deployments like existing ones, but it's on research and it's popular. Uh, 5G that's the latest. We do have implementations for it. There are some implementations for 5G RedCap, which is 5G reduced capabilities. It targets a specific type of devices and that don't need the whole spectrum or the whole bandwidth needs. That's more proper. So that we can use it for um, this specific type of devices that don't need that as much, right? And primary use cases like it's Bluetooth, it's we've mentioned this a lot. Personal devices, audio, earbuds, headsets, IoT sensors, um, that open, close doors, so a lot of domotic stuff. Wi-Fi, home office networking, internet access, high bandwidth applications, and cellular. Uh, Smartphones, wide area connectivity, and critical applications. So if we do like a summary of this table, this is a performance comparison illustration in which we can see Bluetooth is the slowest in comparison with the other ones. The other ones may or may reach the same speed in some applications, but in general, cellular is better. Uh, can be better depending on your application, sorry, because it's clearly faster in Wi-Fi. Range, Bluetooth is for low low distances, and it goes higher on with the protocol, Wi-Fi and cellular. Power efficiency, it's gonna be smarter regarding power consumption in Bluetooth, and then we're gonna have to give a lot more power to Wi-Fi and a lot more for cellular. And a low cost complexity, the Bluetooth tends to be a little bit simpler in terms of hardware and firmware development, but Wi-Fi increases complexity, and cellular for sure makes it the hardest to handle.
Okay, what do you have on the next slide? Because I'm curious. Because um, I think
I
for
have a little bit
talking
on
to modem, it doesn't have to be always difficult. Or so I'm curious.
that's why we get paid the big bucks. Modem technologies now can be we can interact with the modem with something called AT commands, which is basically opening a serial port and sending literal strings of AT bang or AT plus commands that make the modem do things. But what goes below that
That's what costs a
user
lot of
layer,
money.
that's the
Ah,
part that costs a lot of money, and the hardware that you need to make the cellular information exchange, that is what costs a lot of money.
mm-hmm.
Yeah.
So if someone would like to use cellular modem, as we mentioned modem, uh, the user level implementation, it doesn't mean it's complicated. It's not complicated. Because I think when I was doing this, even I think I was using Linux, and there were drivers which can use AT commands to talk to modems, and it means it automatically creates the network, for example.
Yeah. Yeah, like everything, we have modules and we have system on SoCs, system on chipsets. The latter is going to be more complex. You're going to have different processors working with each other. In modules, for example, there is a product, this ESP32.
Yeah,
That
super
one is
popular.
basically, yeah, it's super popular, it's super cheap, like compared to a lot of things that we're going to see here. Uh, and yet it gives you the capability to interact with the modem with AT commands. So in there you can use the Wi-Fi stack that is built within C code, and it's going to be cheaper and easier to use that one in hardware and firmware perspective. But if you need something, if your product not is going to be used for I wanted to say for a more serious application, like what it needs to be servicing, then you're going to need something that is more complex, and
Mm-hmm.
that is going to skyrocket the cost.
Mm-hmm.
Yeah.
I understand. I understand. If you can't use AT commands, if you need to go, I don't know, much faster or much lower level or something, then it's going to
If you,
cost a lot of money.
if you need to look at the whole system, if your router is connecting to
Smartphone.
a host, if your smartphone is doing more than that, your smartphone is for sure not an ESP32. It's usually powered by, for example, Qualcomm
Yeah.
Snapdragon chipsets, right? So those are not modules. Those are complex system on chips that have different processes going on within their own processors.
Mm-hmm. Okay,
Yeah.
so let's have a look here. How many
That's
slides do you
this.
have? Because
I only have four, but we spent a little bit of time on the first one. That's fine. That's fine. I'm not complaining. It's just we can go a little bit faster on this other three. Um, this is basically my jam. Like, you are a hardware engineer. I I think that for hardware engineers, some of this slide may not be as interesting, but it is for me. But it is important to say that even though it may not be interesting, to me, the fundamental principle that we need to follow when we're doing a device that has hardware is do not go into silos because firmware and hardware need to go hand in hand for a good design and to have iterative prototypes that let us know if we're doing something wrong in the early stages. Uh, One of the biggest lessons learned uh, that has ever existed is that when firmware and hardware teams don't talk, things get bad really quickly. Um, so yeah, basically this is a very high level uh, summary of how the code from my firm's perspective is seen. This is not one-on-one OSI model. Uh, it is not, but it one can see some similarities in the horizontal rows that we
Mm-hmm.
see. But basically, what we talked about in the previous slide is application level. That's the highest level of software you're gonna have in your device. So it usually does something different for each stack, and it doesn't really matter because if you're gonna I don't know, if you're gonna uh, stream a video in Wi-Fi and cellular, it's gonna look the same in
Yeah. So
your in
basically,
your
this
phone.
can be, for example, internet browser. Yeah, that's the application
Exactly,
level.
exactly. That's way high, depending on what your device is doing. Uh, so, but the lower stacks, that's where the differences start to appear from a coding perspective. So, Bluetooth works with something called profiles management. H2DP is basically a way to stream audio, high quality audio. So, whenever you're using your headset, that's the implementation that it's using. HFP means hands-free. So whenever you're using a headset with for voice calls and stuff, that's the part that it's been used of the code. And human interface devices, if we have keyboards, mouses, or gamepads that connect via Bluetooth, it usually needs an event-driven implementation
Mm-hmm.
because you don't know when you're gonna do a key strike, right? So keystroke. But yeah, that's the part that is gonna be used of the stack. L2 cap is like a traffic controller for the information that we're sending. I'm not gonna go deep into this. I'm gonna go faster. HCSI is the part that handles interruptions because Bluetooth will need different um, interruption sequences to service the protocol rules. And yeah, that's as far as I'll go there. Wi-Fi, TCP/IP stacks. This does relate a little bit, a lot, well, not a little bit, a lot more to the OSI model from networking. We have the technical specification 802.11 for MAC layer. That is super used for Wi-Fi. Uh, CSMA, we mentioned this here. What the modulation does here is guarantee a quality of service. And that is an interaction between the TCP/IP stack and the MAC layer dynamics. Phi processing, physical processing, how we convert the bits and how we
Oh,
transmit
so
them.
basically, what we are talking about in previous table, then we can see these things here, but they are like above of each other.
Yeah, yeah. The idea here was to show like how they are
Mm-hmm.
stacked
Mm-hmm.
in the stack, sort of saying in the code implementation, how one would see it in an abstraction layer, sort of. Cellular has its own terminology. NAS is non-stratum uh, access, non-access stratum, that handles the session, all the PDU management that we need, the barriers, all those are cellular terminology, how we attach to the network and how we detach from it. RRC is radio resource control, when and how we turn on and off the radio um, that we're using. PTCP, that's packets control. Packet something coverage protocol. I don't remember the P. But basically, it's how the um, similar to when we do TCP/IP, dis how we're using transport layers to distribute the packets. That's the part that does it. And radio link controller is how segmentation is done for those packages, and if we need to retransmit packages. Max scheduler, it's a little bit similar to Wi-Fi. And five physical layer, five means physical. And we mentioned how the modulation is done for this in the last slide, in the previous slide. The parts from the physical hardware. Really hard to think of a cellular or a Wi-Fi device that doesn't have a DSP, a digital signal processor inside of them, because they need to do a lot of math to do the hard work on the mathematical stuff that goes on inside them. And lower low power consumption. We mentioned this before. Low range for Bluetooth, for
Wait.
Wi-Fi.
I would like to. So I would like
Mhm,
to just make summary. So
mhm,
basically, we have so many layers because, for example, we have to start in our application in internet browser where we are basically transferring data, like maybe video. But
mhm.
these our data, they have to be somehow integrated into whole network. So that's why we need another layer which will integrate our data to whole network of all the other devices connected there. And then, for example, we need a layer with this modulation, so we can transfer this data, all the data. We need to change them into signals. So that's why we need another layer, and then we will transfer this signal, correct?
Yeah. This is basically from a device perspective, but if you want to see it as on a whole system level, yes, there are more interactions that going on. But yes,
So we need more layers because every layer is doing something a little bit different.
we need we're going to have more components in the system. So we're probably going to have something similar. For example, in cellular, when you see the block and the NAS, RRC, blah, 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 something similar happens on the base station.
Mm-hmm.
Yeah. So the system becomes more complex. This is just from a device perspective.
Mm-hmm.
Yeah.
Okay, and you started reading the key features.
Yeah, I was doing Wi-Fi key features, high throughput, we mentioned, network infrastructure. You're gonna need an internet service provider there. Um, Modulation becomes more complex. Cellular, wide area, we can service a lot of places now. And complex handoffs. This is interesting. This is something that I didn't mention. So Wi-Fi is usually stationary, if you think of it.
Oh,
Um, you're not moving
moving.
your access point. Your access point is somewhere in your um table, whatever. Cellular, your mobile phone goes through the whole city
If you
with
go
you
in
when you're
car.
traveling. And if you go in a car, that your cellular, your smartphone is going to be moving too. So and even though you're moving, your device is able to get coverage to receive calls. That is something that is interesting. And that happens with handoffs between base stations and frequency bands too.
I remember this was one of problems when cars were moving too fast. Then I think all
Yeah.
generations of phones they had problems with this. Correct?
Yep.
Uh,
Yep. Yes. Um, Okay, processing memory requirements. Again, these are symbolic numbers. They might change from application to application, but
mm-hmm.
the idea and the order of magnitude gives us a correct understanding of why it is needed more for some. for some protocols.
Hmm.
So depending on your chipset manufacturer, you can have different uh, uh, processors. In this case, Bluetooth can do with uh, ARM chipsets of different families, and memory for Bluetooth in terms of storage, flash memory. It's going to be little. You don't need to save that much information. RAM is also little. That's volatile memory. And in contrast with the Wi-Fi, where we're going to need more, we're changing from kilobytes to megabytes for both storage and volatile memory. In cellular, you're going to need a lot more for both. Um, and as mentioned before, difficult to see a Wi-Fi or a cellular device without a DSP because it needs it for all the mathematical computations that it has to do for the protocol. And real time, and this is the part that I mentioned, it was conservative, soft real time requirements. Like we saw it in the latency, but it doesn't necessarily mean that for interrupts, the way the HCI host controller interface part works for Bluetooth is definitely not a soft real time requirement. It needs to have a specific um, time constraint and needs to comply with it in order for the exchange to work as expected. Um, but in general, we saw from a latency perspective that it's lower, it's slower for Bluetooth, but faster for cellular. That's the idea. So it's going to have more strict requirements for cellular. Uh, Development integration considerations, Bluetooth, simple APIs. There are a lot of for Bluetooth. Manufacturers will hide some of the implementation in binaries. Actually, in all protocols, the lower layers of the implementation will be hidden in binary files, so we don't see code. For example, C languages, we don't see it, but we are able to use those binaries because they have created an SDK that allows us to use it. And from that SDK, we can create higher levels for our higher level logic for application layer, depending on what we want to use it for. Uh, but definitely the code that goes within Bluetooth, it's going to be a little bit simpler than Wi-Fi and much more simpler than cellular.
I remember,
So Wi-Fi.
yeah, I remember Bluetooth standard. It actually is not so simple if someone would like to implement it properly. But I know many devices they just end up with like serial communication, and that's how basically people do the data transfer. Because I think they have these profiles what you mentioned. Then you need to select, if you do it properly, you need to select or use the proper profile, and then I don't know, maybe you need to even pay for maybe Bluetooth something, and I have no idea.
Yeah, complexity is a subjective concept, right? In terms of what when I say complexity is meant to cover the amount of lines of code that you need, the amount of binaries you're gonna see, the amount binaries meaning the amount of code that is hidden to us, and yet we need to use it so that the application works. That's the part that is tricky. Manufacturers will provide APIs, but they, due to intellectual property stuff, they will not necessarily tell you how it's working, and yet you
Yeah.
have to make that part work in some for some requirements. Um, that's the part that is. I'm not saying Bluetooth is an easy stack to learn. I'm saying compared to other technologies, for example,
Yeah,
Wi-Fi and
Wi-Fi. I
cellular.
don't know how I would implement Wi-Fi.
Uh, well, Wi-Fi network stack integration, security protocols, performance tuning, provides flexibility in those areas. Cellular, definitely you can have a lot of Wi-Fi devices, pretty easy. You cannot have so many cellular devices so easily because they need to go through certification rounds.
Mm.
So carrier certification, regulatory compliance, multi-standard support, all protocols, multi-standard mean different generations, right? We still have LTE, we have 5G, we're gonna have 5G RedCap, right? Um, So all protocols require careful RF design, electromagnetic interference, and electromagnetic compatibility compliance, and thermal management. Uh, Thermal
You
management
know
is
all the shortcuts. I'm so impressed. I don't remember what the shortcuts they mean. You know almost all of them. I think you only didn't know the one of the RRC. I don't know, or the other one. I don't know.
PDCP, Packet Coverage Protocol. The D, I don't remember what it stands for, but it's complicated to learn all these acronyms. But I think that the acronym gives you a hint of what it is for. So the idea, you get a grasp of it if you learn what the acronym means.
Okay, and key
Um,
differences. So I noticed power management, cellular, dynamic adaptation. That's exactly what I meant when we were talking about changing the power based on, I don't know, distance from the base. I don't know. Correct?
yeah, yeah, yes.
Oh.
I'm gonna change slide now. This is where the hardware engineers are gonna be interested. Because uh,
We
this
are
is
almost there. 1.5 hour. We are almost now. We are almost there
okay. All right,
for hardware design
we're
engineers.
don't worry. No, the first slide is gonna be interesting to them too. It's just the second one. They might just not get that interested, but it's still like it. The idea to share the firmware side is for them to
I'm kidding.
understand
I'm
why we
kidding.
need to work together so closely.
I think
Um,
everyone, everything what we are talking about, it's the background which people never know when they will find it useful, because it's always good to understand a little bit more, only not only what you need, but understand how it works. What are
yeah,
the capabilities? What are
yeah,
these different protocols, possibilities, how it works? Because it can give you ideas.
yeah, yeah. You're selling this talk. Good job, man. Um, uh, yeah, definitely. Like knowledge doesn't take that much space, so that's something we should all strive for in engineering. Um, okay. Common wireless integration failure modes. So what are some issues we see when we're actually seeing the product function? So first of all, power issues, power supply issues, voltage droop during TX. That's not a typo. I'm not an English native speaking. To me, that part was wrongly written, but it turns out a droop is a drop in communication, but it's very small.
Hmm.
Uh,
Oh,
that's
I
why it's
didn't
called
know
droop.
this.
I didn't know it either. But that's a thing. Anyway, connection drops during transmission. That's the symptom that we're seeing in our device. Okay,
This is
so
this is
what's
actually very good point, because many people they have problems with modems. Exactly when modem starts transmitting, voltage may drop if they don't have proper decoupling or good power, and then they will, I don't know, the modem will reset or something.
yeah. Yeah, that's you just summarized what I'm gonna say. So I'm just gonna read it. Cause insufficient
Ah, okay,
volt
I see it now.
capacitance solution, adding more capacitance, right? Near the radio. That's basically a good hardware design. And switching noise, intermittent connection failures, the DC-DC converter noise coupling, linear regulators for radio, other hardware stuff, ground loops, symptom, poor sensitivity, electromagnetic interference issues, multiple ground paths, ground topology is the solution. So basically, all of those power issues usually come from not great hardware designs, and there are best practices to avoid this kind of issues. So those can be followed too. Timing issues. That's a little bit. So some issues. I mean, the beauty of hardware devices is that some issues may be firmware issues, some issues may be hardware issues, and some issues may be a combination of both. So timing issues usually lies on our plate, and because we're assuming that a sufficiently uh, powerful clock was chosen for the for the device. So crystal accuracy, Bluetooth audio dropouts. Uh, we have a crystal of a specific hertz, and then it turns out that the performance is not working well. And I mentioned thermal management in the slide before, but basically, when you stress components with heat, um, we've all seen data sheets where electronic components have the temperature uh, representation. That's why thermal management is important. That is done in a combination with firmware logic and some uh, designs from hardware side. But basically, is try to have that thermal management uh, view, perspective, implementation in place, so that if something gets heat up badly, then your device doesn't go to the drain because of that. Uh, Interrupt latency. We miss the latency numbers that we shared in the first slide. Wi-Fi beacon misses connections, right? So interrupt controller limitations, nested interrupt controllers. I didn't talk a lot about interruptions, just mentioned it a little bit in the previous slide, but basically having sufficient interrupt lines for or peripherals for each of the protocol needs and the application needs, that's going to be helpful for us. Clock domain crossing, cellular timing failures, asynchronous clocks in your UART interface, synchronous clock design, that's a way. Uh, it That doesn't mean we shouldn't use asynchronous methods. That means that if we're going to use it, then we should probably use them in a smart way. Signal integrity issues, that's more from a hardware part. Antenna detuning, symptom reduced range, poor sensitivity, cause enclosure affects antenna matching, and solution antenna tuning in final enclosure.
I created
When
some videos on this topic.
Oh, really?
Yeah.
Cool. That is why early prototyping is so important. And some of the early prototyping will not include final enclosure, but it is suggested to use a similar one at least so that we can start seeing
Yeah,
how
because it
the
will
device
change
is
the
going to behave.
properties.
Yeah,
Yeah.
yeah, yeah. Uh, EMI, EMC issues, certification failures. This is basic regulatory stuff that we need to do for most devices in electrical fields. Inadequate shielding, filtering, proper grounding, impedance mismatch, symptom reflected power, poor efficiency, cost, trains impedance, not a specific ohms, solution, control impedance, printed circuit board. Interface issues. That's firmware hardware stuff. That could be both. So SPI clock issues, data corruption, timeouts, clock edge timing violations, proper setup, fault margins. So SPI is a specific protocol that we use to exchange data. The way it works, um, if we don't implement it, there is usually already an implementation from the manufacturer. But if there is a bug in the protocol that is not couched, then we're gonna have problems when we use this one.
Mm-hmm.
I squared C bus lockup, symptom, communication hangs, cause clock stretch and timeout, solution bus recovery mechanism. So we we basically do implementations based on falling and rising ages of signals. So in I2C, there is a way in which a slave device can tell the master, I'm not ready to receive data, so just hold on for me. And they put the clock line low so that we don't get any more data for the slave. And that, if we do that for a longer time than what we need, that's when clock stretching comes into place because we're gonna have some issues in the
Yeah.
communication. There's gonna be fallouts, and that's why bus recovery mechanism is suggested. UART flow control, symptom buffer overruns, data loss, cause hardware flow control ignored. Solution proper CTS RTS implementation is suggested. Okay, and real world case studies. no, they have not happened. I cannot say if they had happened or not to me, but I'm gonna say it anyways. Um, and so case study one, Bluetooth audio dropouts. Uh, so it is extremely frustrating not to hear your music fluently. Uh, Audio stuttering every 30 to 60 seconds. That's a problem. The investigation was a logic analyzer showed missed connections events, root cause, Wi-Fi activity blocking, Bluetooth interrupts. There are some devices
Microwave.
that in order microwave, but there are some devices that are curious, dependent on the hardware design they are not allowed to use Wi-Fi and Bluetooth at the same time. If we use laptops, if we use desktops, it's easy. You just enable both
Yeah,
with
yeah, yeah, yeah.
the UI, whichever OS you're using, and it's allowed. But there are some chipsets that even though you get the two features, you cannot use them
Mm-hmm,
simultaneously
mm-hmm, mm-hmm.
because the hardware design has interrupts that are dedicated to be used only by
Yeah, yeah.
one one
I've seen these chips. Yeah,
Yeah, yeah. So that's interesting. If you're gonna choose a chipset that needs both stacks working, then you need to make sure you can use them
yeah.
simultaneously. Separate interrupt priorities, isolated domains, dedicated hardware freeze, dedicated interrupt controller with nesting. Case study two, Wi-Fi throughput degradation. This
Maybe
is
here was the microwave, no? Because I'm mentioning this because I know sometimes when we use microwave, then internet will drop.
Yeah, yeah, yeah. Even with your headphones, right? Remember we share a little bit of 2.4.
Yeah,
So if you have any Bluetooth device, you're gonna feel the same thing.
yeah. Because I think we would like
Uh,
to point out microwave is using 2.4 too. But it should not be
uh,
happening because microwave theoretically should be completely safe and no signal should go out.
y- yeah, that's the theory, right? The practical implementation always differs a little bit. Um, uh, just really quickly, problem expected 10 megabits per second, achieved only 1 megabit per second. So that's a clear degradation of your performance. Investigation, direct memory access bandwidth monitoring showed saturation, root cause, a single direct memory access channel shared with other
Mm-hmm.
peripherals, solution dedicated channel for Wi-Fi transmission and reception. Hardware fix, dual channel DMA controller. So basically that's adding another hardware component. But again, whenever we're creating a product, um, this is a matter of cost. As if you keep adding hardware components, it's going to get more costly.
Yeah,
But it is going to
then it
solve
works.
some issues. Yeah, yeah, it's going to solve some issues on the long run. And well, case study three, cellular connection stability problem, random disconnections every few hours. You mentioned this, I think, a couple of slides ago. Investigation, power consumption spikes during TX, root cause, voltage droop, causing modem reset solution. Of course, if the modem is resetting, it means it's not active, so you're not. That's why you see those disconnections. Solution, larger bulk capacitors, improve power supply, hardware fix, just add more capacitors, more
Mm-hmm.
and with uh, higher capabilities. Uh, and finally, prevention strategies and design lines. These are high-level recommendations. Power supply design. Use linear regulators for RF sections to minimize noise. That's best practice number one. We want to minimize interference and noise in all signals that we're using. Uh, add
Where
bulk
did you
capacity.
find this? I'm just curious because you are expert for firmware development.
I've worked in different projects. I haven't. I cannot. That's why I said I cannot say or not say that I've seen them because that means we found something that we needed to fix in a product, and that looks bad. But no, yeah. I mean, it's discussions with has been some experiences with projects, and parts have been
But I've
discussions
seen
with
these
other
problems.
teams.
I
Yeah.
know them. Yeah, everyone who is starting
Mm.
with this kind of designs, they will experience these problems, and then they will learn.
Oh, okay. Then, well, I need to expand my circle. Yeah, yeah, it's we've seen it from in some products. Uh, uh, Power supply design,
Yeah, I
last one.
interrupted you.
No, that's totally fine. It's a conversation. Monitor power consumption during development, signal integrity, use control impedance PCBs, keep RF traces short and minimize bias, perform antenna tuning and final enclosure, include test points for critical signals, uh, use hardware flow control for your interfaces in interface design, implement proper pull-up resistors for I2C, and series termination for high-speed SPI, design for debuggability with test points. Key takeaways. Most integration failures are preventable with proper hardware design and, of course, with proper firmware design, of course, as well. Early prototyping and testing can catch issues before production, and close collaboration between firmware and hardware teams is essential. That's the key takeaway that I started with. The worst problems that I've seen is when firmware and hardware teams don't collaborate.
Hmm.
Uh,
Next slide. The next one is the
Next,
last one.
yeah. Oh, and I forgot to mention, I don't remember what CTS means, but RTS means request to send. Those are hardware flow acronyms for the UART protocol. But
Yeah,
anyways,
I think many people they don't use them, but for modems, you
yeah,
should use
they don't.
them.
Yeah, yeah, exactly. They are not as popular in normal applications, but they are when you need to um have a robust design.
Yeah,
This is the last slide. It's basically just a
summary.
summary of what we just discussed. It's presented in a flow diagram. So we're trying to see which wireless stack, which wireless component we're going to use for our application. So we need to know budget as always, and if we need to be using devices that need to last a lot of time with battery. So these are applications where you would have devices that are on remote locations that cannot be maintained in a regular basis. So that if it gets uh, turned off for some reason, it's going to be really costly to get someone there to replace whatever is wrong
Hmm.
with that, right? So that's question number one. If it is, then if it needs to last a lot of time, then we're probably gonna need to use Bluetooth because it has the best power consumption strategy, right? And so it's gonna last a lot of time. And that's the part that I mentioned about modules versus systems on chips. Uh, if you're gonna use a simple module, then you can have in your applications less than 10,000 devices. If you have a bigger volume in which you will need more devices that need a little bit more processing power, then you're going to need an SoC. So that means you're also going to be facing some certification processes depending on what you choose. Uh, if we go back to if the device doesn't have a battery or doesn't need to last that long, then how much data do you want to transfer? How much data do you need to transfer? How fast do you need to transfer it? Um, if it's a relatively not high demanding application, then you can see in terms of distance which protocol you want to use. Is it short distance? Then we can probably use Bluetooth. If it's medium distance, 10 to 100 meters, maybe Wi-Fi, maybe a little bit longer than that. But if it's going to be a large distance, then you can have cellular technology. If your device is going to need a lot of power and is going to need it because it's going to transfer a lot of data, then you're for sure gonna need Wi-Fi or cellular, depending on your product. Um, that means that you're gonna have the infrastructure so that your device can connect to the network, eh, external infrastructure, so that your device can connect to the network. Local network, a Wi-Fi module, wide area, cellular modem, cost, Wi-Fi NRE or cellular OPEX. That's again infrastructure, all infrastructure terms. Um, Implementation details and firmware considerations. These are just some examples from some manufacturers out there.
Mm-hmm.
Uh, from
Bluetooth
these,
ESP32, and we
exactly,
already
from the
mentioned this. But the
tiny
Nordic
module.
chips are also very popular.
Yeah, yeah, they are. They are easy to use. They have already a lot of APIs. They have some good client implementations already that are pretty then enough there's enough code for you to do some interesting things. So um fast development, pre-certified, limited customization, higher costs. SoC approach, you have bigger chips, you have more chips inside your product, so it's going to be more costly. And TI, that's Texas Instruments, that's another manufacturer. uh, Pros, you have full control, lower cost at scale. Cons, RF expertise is needed. You need to have more knowledge to, or at least have more experience with this type of chipsets, to be able to do a simple application. Certification for sure. Wi-Fi implementation, ESP offers that. The code is open. You can use it with any uh, open source. There are actually a lot of open source projects already ready. Um, Pros, integrated TCP/IP crypto, so it has, as I said, there is some code already for you to use. Power consumption, cons, and limited GPIO. Chipset approach, Broadcom or Qualcomm firmware, custom network stack. So this is where I mentioned some manufacturers will hide the intellectual property, so you're not going to be able to see all that is happening, but you still need to understand the black box so that you can use it for your application. And cons, complex integration, driver support. Finally, cellular implementation, module approach.
Semtech. Ah.
This is a commercial. This is an overt commercial because I work there. But basically, firmware, there are more than one way to interact with the routers that we build, but that the company builds. But one of them is AP command interface when we're working with a specific module inside a router. So pros, simple integration, certified. Cons, limited power control, cost. It's if you need to use a router, it means you're doing something that the application needs a lot of a lot of data to transfer. So it's not uh, usually it requires a lot of investment because you're doing something that requires to have a lot of data going in and out. And chipset approach, Qualcomm is one of them. We see them in smartphones, right? Most smartphones have Qualcomm chipsets, and they have a lot of years doing cellular technology, so they have a lot of 3GPP policies already in place in the code. And pros, full control optimization, cons, extreme complexity time. It's repositories of code can become very, very um, big, very elaborated. So
I
understanding
guess also
those.
not everyone can actually probably work on this kind of level implementation.
Yeah, if you it usually requires a license. You need to have a partnership with
Hmm.
the manufacturer that you're working with. In this case, for example, Qualcomm requires partnerships. So the code is not open.
That's what I thought.
Yeah, yeah. And finally, we mentioned a little bit about cost in the first slide, cost analysis and decision factors. Uh, Again, these are symbolic numbers. It doesn't, they can differ a little bit, but
Hmm.
the order of magnitude and the significance is what's important. If we see development costs meaning people. training people, having hours of R&D invested on that, early prototyping, all of that. If we're doing a device based on Bluetooth, it's gonna be cheaper than when you do it with Wi-Fi, and it's definitely gonna be cheaper than when you do it with cellular. Certification costs, it's very expensive for cellular, and it goes down
200K, it can be 200K.
it can be 200K depending on what the project needs, depending on the technology that is being used, Wi-Fi, and it's gonna be lower, and Bluetooth is gonna be much lower. Component costs, as a general rule,
Yeah,
if you just need
ESP32
Bluetooth, it's
$4.
cheaper. Yeah, I mean, Wi-Fi, you can find something that is workable and yet still manageable, but cellular is huge. The
More
cellular is
expensive.
not a cheap
Yeah,
technology,
yeah.
so it's gonna be more expensive in general. And that's what I prepared for you
Did I have many
today.
questions?
Do I have any
Me,
questions?
did I have many
Oh,
questions?
oh, no, I mean, you did. I mean, yeah, yes, you did. Um, they were good questions. They were good questions.
Thank you. No, thank you for preparing these slides because it looks like these are only for slides, but actually there is a lot of information. When I went through your slides just to collect all this information, I think it was a lot of work, no?
Yeah, yeah, it took a weekend from me. Thank you, man. No, I mean, if there is so much information out there, and the different generations change some things. So trying to summarize what is important to understand that is different between generations, but it still be able to just mm, make the key points so that we understand how the latest generation works. I think that's the part that was a little bit tricky, and that's why I made specific comments on some blocks, because there is definitely, even though we talked for pretty much 2 hours
2 hours.
now, there is so much in depth that we didn't go to. But the idea of this conversation was to have just a high level
Yeah,
understanding of how these protocols differ from each other, and how some firmware hardware uh, uh, experiences happen when when we're actually working with a real product.
yeah. I think just having the comparison uh, side by side is very useful. Like, I don't know, distance or this kind of data rates or something like this, because otherwise I never really thought about it. I never really like intentionally went and searched for what is the maximum data rate for Bluetooth, and then I went, what is for the cellular?
Yeah. Yeah, and it's gonna keep evolving, right? The technical specifications keep evolving again. So when we're having today this talk, maybe next generation is already ready and it has improved, right? So
Tomorrow, Wi-Fi 7,
maybe there's tomorrow that
and
they
the video
release
is outdated
Wi-Fi
now.
7.
I'm just
But that is going
kidding.
to happen with any technology. But the idea of the numbers is to give a significance of why they differ, more than the specific number that is given.
Yeah,
Yeah.
yeah, exactly. Thank you so much, Frida, for preparing this. As I said, you really spent a lot of time preparing this, so thank you very much.
No, on the contrary, Robert, it was a privilege being here. I appreciate the time, and I really enjoyed this conversation. Thanks so much. You made it really late.
That's all for this video. I hope it was helpful. If you would like to learn more about electronics and board design, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KeyCAD, and also courses covering many different topics, for example, FPGA, EMC measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching, and don't forget to leave your comments. See you in the next video. Bye.